Reproduce the scattering of alpha particles, provide evidence for the structure of the atom. Sketch a label diagram showing experimental arrangement of the apparatus used by Rutherford. Part I, 2 marks. Second part, II, state and explain the results of the scattering experiment, your answer including main observations, significance of each observation, and how the observations, there's no A in it, observations placed an upper limit on the nuclear radius. That's for 6 marks. It says quality of written communication, which isn't really actually included in the spec anymore. But the question's still valid in terms of the content. So let's start off. Part I. Oops, let's jump across to the camera. So part I then. Overall, this whole experiment is going to be taking place with inside something that's a vacuum. So we've got a vacuum container. So there's my vacuum. And in there, first thing let's actually draw is, let's draw our gold leaf. So I'm actually going to draw the gold leaf in terms of a set of atoms. The reality is it is not one atom thick. It is way, 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 way more than one atom thick, despite gold being incredibly malleable. So gold leaf, but it's pretty good. We get it as thin as we can. And over here we're going to have our source. So that's my source. And around the source then we're going to have what's called a collimator. So the source emits alpha radiation omnidirectionally, in all directions equally. However, by having this column, this around it actually absorbs the alpha particles going any direction other than down this hole. And these go down the hole, and so you get a very nice narrow beam of alpha particles. So that is called our collimator. Alright, now, the next thing we've got to be able to do is detect where these alpha particles actually go. So some of them are going to be deflected off. Let's say some deflected in that direction. And I'm going to have my detector. So this is an alpha detector. And what I'm actually going to want to do with that is I'm going to want to move that around. So I can actually kind of move it to various places. So I can be measuring these different angles, theta, in terms of its scattering. So for example, I can measure the number of scatters in this direction, 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 as I changed it all the way around. Okay, so that's a label diagram showing me the apparatus I would actually use. The second part then, part II. What I've got then is, there was 3 things it's asked us for. It wanted the main observations. It wanted the significance of the observations, and it wanted the upper limit on the nucleus radius as a result of these observations. So we've got 3 things. This was 6 marks. Now the first thing I would say overall is we've got to make sure we actually attempt each of these 3. If you miss one of them out, you normally get penalised pretty heavily. So we're going to make sure we cover all 3 elements of them. So first off, in terms of things we're going to say, well, most alpha particles passed straight through the gold leaf. So that's our observation. And that suggested, suggesting that atoms are mostly empty space. And that's the significance of our observation. So we've done one main observation, one significance of that observation. The second one we're going to do then is a few alpha particles are scattered by more than 90 degrees. And what I mean by that is they've come here and they've come back, not this side of the gold leaf, but this side of the gold leaf. So they're changing direction by more than 90 degrees. So a few alpha particles are scattered by more than 90 degrees. Suggesting. So we've got the observation. Here's the significance of it. So it's suggesting they have been repelled by a concentrated positive charge. Because it have to be charge positive to repel an alpha particle that is positive. They've been repelled by something more massive than themselves. So basically, if the alpha particle was huge, or had a huge amount of mass compared to the nucleus, it would basically have more effect on the nucleus, push the nucleus out of the way. What we're actually seeing here is the alpha particle is actually effectively being repelled, scattered back. Therefore, the mass of the alpha particle is much smaller than that of the gold nucleus. So again, we've got an observation and we've got significance. Third bit then we've got to do is actually then we'll talk about this upper limit. And the way we're going to do that is we're going to use the idea of a closest point of approach. So what I've got is an alpha particle coming in that does that, basically does that. So that's the alpha particle. And then here I've got a nucleus. And that comes in. Now here you can imagine this point here is the closest point of approach. And this distance here then we're then going to call R. Now this then forms the upper limit for the radius of the nucleus, that distance that we've actually got there as R. So if we look at it then, the alpha particles, first off we've got the alpha particles are not hitting the gold nucleus or gold nuclei. Because they are bouncing, or so they are being scattered back unaffected by the strong nuclear force. So if they got within range of the strong nuclear force, what would actually happen then is they would become attracted to the nucleus. The strong nuclear force, certainly at short distance, is stronger and therefore would actually capture that alpha particle. So you wouldn't see it scattering. Or as a minimum, it's going to deflect its path quite significantly. Okay, so the closest point of approach forms the maximum radius of a nucleus. So the closest point for the maximum radius of the nucleus. And what we can then do is we can actually work that out. So as the alpha particle approaches the nucleus, it loses kinetic energy, gaining electrical potential energy. So it's losing Ke, so it's coming out, slowing down, slow. At the closest point of approach, it is stationary with 0 Ke. Therefore, the closest point of approach can be found from And we've got, so what we'll be saying is half the mass of the alpha particle times the speed of the alpha particle squared at the start. So this would be at when it's emitted. That's emitted. Would have to be equal to QV, where Q is the charge on the alpha particle, which would have to be equal to Q on the alpha particle, Q on the gold, divided by 4 pi E naught R, where R is the closest point of approach. Hopefully that makes sense. Thank you very much.